The Mississippi River, this is also incredible, has hit historic low levels due to the current drought.
At first, nothing about it looked dramatic. No collapsing banks, no sudden flood, just numbers. And that's what made it terrifying. For more than a century, the Mississippi River has been measured with obsessive precision. Water enters at Cairo, Illinois. It flows south. It exits near the Gulf. That's how rivers work. That's how physics works. And for nearly 100 years, the math always balanced. Until it did. In late 2024, engineers reviewing routine gauge data noticed something that shouldn't exist. Water flowing into the Mississippi at Cairo never showed up downstream at Baton Rouge. Not delayed, not slowed, just gone. At first, they assumed an error. That's always the answer when numbers look impossible. But the Mississippi isn't monitored by guesswork. It's watched by 271 continuous U.S. Geological Survey stations, collecting data every 15 minutes, non-stop since 1928. This is the most detailed river monitoring network on Earth, and all of it was saying the same thing. Between mile marker 953 and mile marker 233, the river was losing nearly 200 billion gallons of water every single day. That's enough water to fill Lake Tahoe once every 11 days. A volume so massive, it defied the most basic law of nature, conservation of mass. Water doesn't vanish, yet the data insisted it had. This wasn't happening during a historic drought either. Rainfall across the Mississippi Basin in 2023 was almost exactly average. Snowmelt behaved as predicted. Tributaries flowed normally. Evaporation stayed within expected limits. But the river itself was shrinking. Satellite images from NASA's Terra satellite confirmed what the gauges were reporting. On October 17, 2024, sections of the Mississippi were measured at less than 3 feet deep. Sandbars surfaced that hadn't been exposed since record-keeping began in 1872. A change that should take thousands of years had unfolded in less than 18 months. And the consequences were immediate. Barges carrying nearly 60% of America's grain exports ran aground, stranded on newly exposed sand. Some never moved again. A river that normally transports $700 billion worth of goods each year slowed to a crawl. Entire sections became unnavigable. At Tarbert Landing, Louisiana, the last major measurement point before the river fans into the delta, flow rates normally sit between 400,000 and 600,000 cubic feet per second. That's the equivalent of an Olympic-sized swimming pool rushing past every 3 seconds. In late 2024, those numbers collapsed. And here's the part that alarmed engineers the most. The Mississippi isn't a wild river. It's one of the most engineered water systems on the planet. Over $15 billion has been spent on levees, spillways, control structures, and flow regulation. The Old River Control Structure alone manages the river's path with machine-like precision. This river is supposed to be predictable. Contracts, barge prices, water bonds across 10 states. All of it depends on those flow numbers staying within a tight margin. And for decades, they did. The margin of error stayed below 12%, sometimes far lower. Now, the error wasn't 12%. It was existential. Engineers double-checked upstream inputs. They modeled rainfall. They calculated withdrawals. They re-ran simulations that had been accurate to within 1 inch of water level hundreds of miles downstream. Nothing explained the deficit, which meant the question had changed. It was no longer, is the Mississippi drying up? It was, what is swallowing the water? And whatever the answer was, it wasn't something any textbook had prepared them for. Because rivers don't lose this much water unless something beneath them has fundamental. The moment the numbers stopped making sense, the Mississippi stopped being an abstraction. It became personal. In September of 2023, Dr. Amanda Winters, a senior hydrologist at the United States Geological Survey's Water Science Center in Baton Rouge, was overseeing what should have been a routine discharge measure. Her team performs these tests every month. Same equipment, same procedures, same river. Nothing about that day suggested history was about to break. Using acoustic Doppler current profilers, underwater sonar systems that measure water velocity across the entire width of the river, the team began calculating discharge. The process is simple in theory. Measure speed, multiply by cross-sectional area, and you get flow. The incoming numbers from upstream were clear. At Memphis, the Mississippi was carrying 312,000 cubic feet per second. Based on tributary inflows and evaporation, Baton Rouge should have recorded closer to 340,000 cubic feet per second about a week later. Instead, the number on the screen froze at 287,000. At first, Winters assumed an instrument failure. That's the only rational response when math collapses. Sensors drift, software glitches, calibration errors happen. So they stopped the run. They checked the equipment, recalibrated the Doppler, repeated the transect, then ran it again. Same result. They swapped instruments, verified verified the acoustic profiles, sent samples for independent verification. Every safeguard built into federal hydrologic measurement was triggered. Nothing changed. The water was missing. By December 2023, the loss rate had climbed to 89,000 cubic feet per second. That's not a rounding error. That's an entire major river system disappearing into nothing. And by March of 2024, the loss jumped again. 143,000 cubic feet per second gone over roughly 600 miles. To put that in perspective, the Mississippi was losing water at a rate comparable to the entire flow of the Colorado River, and it was accelerating. There was no corresponding drop in tributaries, no massive upstream diversion, no spike in municipal or agricultural withdrawals large enough to explain it. The numbers weren't drifting slowly, they were breaking faster with each measurement cycle. Winters documented everything. Her reports didn't accuse, they didn't speculate, they simply stated the impossible. The volume of water entering the river did not equal the volume leaving. Behind closed doors, the implications were obvious. If the data was right, then one of two things had to be true. Either the most reliable river monitoring system in the world had failed all at once, or the Mississippi River itself was behaving in a way that violated every assumption modern hydrology was built on. And that's when concern turned into urgency. Because once the loss rate crosses a certain threshold, it stops being a scientific curiosity. It becomes a systemic threat. Barges stop moving, contracts collapse, municipal water intakes fail, ecosystems unravel. This wasn't the problem for the future, it was happening in real time. By early 2024, Winter's findings could no longer be handled quietly within the Baton Rouge office. The data was forwarded upstream, then sideways, then upward through federal channels that rarely move fast. And when the message finally landed on the right desks, the response was immediate. An emergency review was called, because if one scientist was right, everything the system depended on was wrong. And what they found next would shake every assumption about how the Mississippi. By April of 2024, the problem was too large to ignore and too dangerous to misinterpret. The U.S. Army Corps of Engineers convened an emergency technical review board. 37 specialists were pulled in from across the country: hydraulic engineers, geologists, climatologists, and river system modelers. These were not outsiders. They were the people who had spent their careers shaping, stabilizing, and predicting the Mississippi. 18 months of data were placed on the table. Every gauge between St. Louis and New Orleans, every discharge measurement, every satellite observation, every model output. The mandate was simple: find the missing water. The review started with the obvious assumptions: instrument failure, calibration drift, software inconsistency between monitoring stations. But station after station confirmed the same thing. Independent systems, run by separate teams, produced identical deficits. The data wasn't noisy, it was clean, and that made it worse. The Corps cross-checked the figures against climate models from the National Center for Atmospheric Research. These models had previously predicted Mississippi water levels hundreds of miles downstream with 94% accuracy, often within a single inch. Snowmelt timing matched expectations. Rainfall inputs aligned with historical averages. Groundwater inflows behaved normally. Nothing was wrong upstream. Yet downstream, the river was collapsing. At Tarbert Landing, the last major measurement point before the Mississippi spills into the delta, flow rates had historically fluctuated between 400,000 and 600,000 cubic feet per second. This rhythm was so reliable, it formed the backbone of shipping contracts, barge pricing, water bonds, and interstate allocation agreements across 10 states. Now, those numbers were breaking records in the wrong direction. The internal review report contained dozens of charts, graphs, and statistical confidence intervals. But buried inside the technical language was a single conclusion that stunned everyone in the room. Measured losses far exceeded natural variability and any known human extraction by a factor of 6.7 to 1. There was no precedent for that number. In hydrology, uncertainty is expected. Rivers fluctuate. Models have margins. But a discrepancy this large doesn't suggest error, it suggests a missing process, something fundamental that no one had accounted for. And that's when the language began to change. Engineers stopped using words like temporary and anomalous. Briefings replaced certainty with phrases like inconsistent with established aquifer behavior and not explained by current hydrologic frameworks. In closed meetings, researchers admitted what they would never say publicly. If the data was correct, then the Mississippi wasn't just losing water, it was redistributing it in ways that contradicted everything they thought they knew about North American river systems. At a closed symposium at Tulane University, Dr. Amanda Winters put it bluntly: if this interpretation holds, she said, then every hydrology textbook used in North America is incomplete. That statement didn't make headlines, but inside the room, it landed like a warning shot. Because once a system behaves outside its theoretical boundaries, prediction collapses. And when prediction collapses, control disappears. years. The review board didn't issue a solution. It issued a realization. They weren't dealing with a drought. They weren't dealing with mismanagement. They were dealing with a river that was no longer obeying the rules that had followed for centuries. So the focus shifted. If the missing water couldn't be explained by traditional hydrology, then the only option left was to test every explanation that theory said should work. And one by one, those theories would begin to fail. Because the mystery of the Mississippi wasn't happening above the surface. It was happening when a system this large breaks. Scientists don't jump to extreme conclusions. They start with the boring ones. The review board divided the mystery into categories. If the Mississippi was losing water, it had to be leaving through a known pathway: agriculture, evaporation, geology. Each theory was tested, modeled, and stress checked. The first suspect was agriculture. The Mississippi River Basin supports nearly $60 billion in annual agricultural output. Rice in Arkansas, sugarcane in Louisiana, soybeans, corn, and cotton stretching for hundreds of miles. Irrigation uses enormous volumes of water, and in a dry year, those withdrawals can spike. So researchers pulled groundwater data from over 14,000 agricultural wells across the basin. The numbers were clear. In 2023, total agricultural groundwater use averaged 8.1 billion gallons per day. That sounds massive until you do the math. Even at peak usage, it explains only a fraction of the missing water. Worse, agricultural withdrawals in 2023 were lower than in previous years due to reduced cotton acreage. If farming were the cause, the river should have been recovered, not collapsing. Theory 1 failed. Next came evaporation. If rising temperatures were pulling more water into the atmosphere, satellites would see it. NASA's EcoStress thermal imaging system was used to calculate evapotranspiration across the basin. Evaporation plus plant uptake. The result? Evapotranspiration was 2.3% above the 30-year average. That increase translated to roughly 4,000 cubic feet per second of additional water loss, not 143,000. Evaporation wasn't even close. Theory 2 failed. Then came the explanation that made people uncomfortable. What if the water wasn't leaving the system at all? What if it was draining underground? The lower Mississippi River Basin sits atop layers of limestone and sediment known to form karst features, underground voids and channels capable of moving water rapidly into deep aquifers. If a new collapse or fracture had formed beneath the riverbed, it could act like a massive drain. To test this, a joint team from Tulane University and the University of Memphis launched an extensive geophysical survey. 127 seismic sensors were installed along the river corridor from Memphis to Vicksburg. Controlled vibrations were sent into the ground, creating acoustic images of the subsurface down to 2,000 feet. If giant underground cavities existed, this would reveal them. It did. No new karst systems, no fracture zones cutting through the confining clay layers, no hidden caverns large enough to swallow a river. The geology matched surveys from 1997 and 2012 almost exactly, except for one detail. Beneath the riverbed itself, something had changed. The seismic data showed a dramatic increase in porosity, the amount of empty space between sediment grains, in the unconsolidated sand and gravel directly below the river. Normally, porosity in these deposits ranges between 28 and 33%. In 2024, values between 41 and 47% were recorded. That kind of increase doesn't come from erosion or collapse. The sediment wasn't disappearing, it was reorganizing itself. Dr. Michael Reeves, a sedimentologist at Mississippi State University, described it this way: the riverbed wasn't breaking apart, it was rearranging itself to hold more water, like a sponge forming from inside. At first, this seemed promising. Higher porosity means more storage. More storage means water can move into sediment before continuing downstream. But there was a problem. Porosity doesn't destroy water. Once sediment fills, it saturates. Flow should resume, unless something is pulling that water away as fast as the river can feed it. And that realization forced the review board to confront a far more unsettling possibility. What if the Mississippi wasn't leaking into the ground? What if it was being drained? Because the next theory did. The moment researchers stopped asking where the water was going and started asking what was pulling it, the picture finally began to sharpen. Beneath the Mississippi River lies a massive interconnected groundwater system. Two aquifers dominate the region: the Mississippi River Valley Alluvial Aquifer and the Memphis Sand Aquifer. Together, they supply drinking water to more than 8 million people across Arkansas, Mississippi, Louisiana, and Tennessee. They've been pumped continuously since the 1960s. Municipal wells, agricultural wells, industrial withdrawals. Decade after decade, water was removed faster than it could be naturally replaced. The decline was slow, measured in feet per year, and easy to ignore, until the river responded. Hydrologists have a name for what happens next: induced recharge. When groundwater levels drop, they create a pressure gradient. Water moves from areas of higher pressure to lower pressure. If a river is connected to an aquifer, and the Mississippi is, the river begins feeding the groundwater system. Usually, this happens at a manageable scale. This time, it didn't. The USGS Memphis office analyzed water table elevations from 892 monitoring wells across the lower Mississippi Valley. The results were staggering. By 2024, groundwater levels averaged 23 feet lower than they had been in 1990. That drop created suction, and when that suction met a riverbed whose sediments had suddenly become more porous, the Mississippi found itself pouring water into the ground at a rate no one had ever modeled. The math finally worked. Groundwater withdrawals increased. Aquifer pressure dropped. Riverbed porosity expanded. Together, they formed a hydraulic trap. The river wasn't drying up because it lacked rain. It was bleeding into its own groundwater system. And the faster the river tried to feed the aquifer, the faster the aquifer pulled it in. By late 2024, the numbers aligned perfectly. The missing discharge wasn't missing at all. It had simply moved from surface flow into underground storage. Billions of gallons per day slipping into sediments and aquifers that release water on geological timescales, not human ones. But solving the equation didn't bring relief, it brought fear. Because if this explanation was correct, then the implications were enormous. It meant that a century of engineering decisions, levees, dams, channelization, flood control, navigation improvements, had gradually altered the balance between surface water and groundwater. No single project broke the river. Thousands of reasonable decisions did. Each well drill, each control structure installed, each attempt to stabilize the river's behavior. Together, they rewrote how the Mississippi interacts with the ground beneath it. The river had become a delivery system for groundwater recharge, not a conveyor of water to the sea. And once a system reaches that state, reversing it isn't simple. You can't just turn off the suction. Aquifers don't rebound on command. Sediments don't reorganize overnight. The Mississippi had crossed a threshold. And while scientists debated terminology and mechanisms, life along the river was already changing. Because when a river loses this much water, for decades, the damage stayed out of sight, beneath the riverbed, beneath the soil, beneath the assumptions. Then in 2024, it broke the surface. The lower Mississippi River Basin is one of the most biologically productive regions on Earth. Its fisheries, wetlands, and floodplain forests evolved around predictable flow patterns. Not just how much water moves through the system, but when and how fast it moves. When those flows slowed, the ecosystem didn't adapt. It collapsed. In Louisiana, dissolved oxygen levels in backwater channels dropped dangerously low. Without enough flow to stir and replenish the water, oxygen fell towards zero. Fish that had survived floods, storms, and pollution for generations began dying in place. By June of 2024, the Louisiana Department of Wildlife and Fisheries reported a 64% drop in commercial channel catfish landings. Paddlefish larvae failed to survive entire spawning seasons as currents weakened in the streams they depended on. Across the basin, over 120 fish species lost access to the hydraulic cues that guide feeding, migration, and reproduction. The river wasn't just shrinking, it was suffocating. Along the banks, bottomland hardwood forests, cypress, oak, and tupelo began to fail. These trees rely on annual flood pulses to regenerate. Without floods, invasive species moved in. Native seedlings failed. The forests that stabilize riverbanks and support wildlife started to unravel from the inside. Then the economic consequences arrived. The Mississippi normally carries 500 million tons of cargo every year. Barges are designed around depth. Lose depth and you lose capacity. A barge that hauls 1,500 tons at an 11-foot draft can only carry 1,000 tons at 9 feet. In August 2024, shipping companies cut loads by an average of 35%. Grain shipping costs from Iowa to Louisiana surged 71% almost overnight. Farmers absorbed the losses through lower prices. Consumers felt it through higher food costs. Ingram Barge Company idled 38% of its fleet, and 4 smaller operators filed for bankruptcy. At the Port of South Louisiana, the largest tonnage port in the Western Hemisphere, cargo volume dropped 41% in a single quarter. Every million tons lost erased $120 million in economic activity and roughly 400 jobs. And the damage didn't stop there. Cities that had relied on groundwater for generations felt the squeeze next. As aquifer levels fell, pumping became harder and more expensive. Memphis, which withdraws 180 million gallons per day from the Memphis Sand Aquifer, saw water treatment costs climb sharply. New Orleans, drawing 130 million gallons per day from the alluvial aquifer, faced similar increases. By mid-2024, 3 Louisiana parishes mandated water conservation. Memphis asked residents to reduce lawn irrigation. Vicksburg halted new commercial construction that would increase water demand. A river problem had become a municipal crisis. Insurance companies began recalculating flood and agricultural risk. Municipal bond ratings tied to water utilities were downgraded. Property values in in river-adjacent communities declined as buyers questioned whether long-term water access could be guaranteed. Nothing collapsed all at once. It was a slow squeeze, a quiet erosion of confidence in a river system that had supported life and commerce for 2 centuries. And once the consequences became visible, pressure mounted for action. The public wanted reassurance. Industries wanted timelines. Governments wanted solutions. When a system this large starts to fail, doing nothing isn't an option. In September of 2024, the Army Corps of Engineers announced what it called a recovery initiative for the Mississippi River. The message was calm, reassuring, familiar. Dredging crews would work around the clock to keep navigation open. States would reduce groundwater extraction. Wetlands would be restored to capture and store water. Dam operations upstream would be adjusted to release more flow into the river. More than $2.3 billion was allocated to stabilize the system. On paper, it made sense. Agricultural leaders from 7 states met in Memphis to coordinate implementation. National farm organizations pledged cooperation. The Corps projected that a 20% reduction in groundwater use, combined with improved releases from Missouri River reservoirs, could restore 40,000 cubic feet per second of flow within 18 months. Cities followed suit. Memphis committed $75 million to upgrade water infrastructure and reduce leaks. Louisiana's governor formed a Mississippi River Sustainability Task Force with emergency authority over municipal water use. Congress approved an $800 million drought relief fund for farmers and ranchers. Confidence returned. Barge companies delayed costly upgrades, expecting normal operations to resume by 2026. Farmers planted crops assuming irrigation allocations would hold. Water utilities drafted 20-year plans based on projected aquifer recovery. The public believed the system was under control, and history supported that belief. American engineers had solved water crises before. The Tennessee Valley Authority, the California State Water Project, the Colorado River Compact. The Mississippi, people assumed, would be no different. But rivers don't respond to confidence. They respond to physics. The first cracks appeared quiet in November 2024. As groundwater restrictions tightened, farmers adapted faster than expected. Instead of pumping from wells, many began building infrastructure to withdraw water directly from the river and its tributaries. Surface water intakes multiplied rapidly. In just months, 2,700 new permits were issued across Arkansas, Mississippi, and Louisiana. The models hadn't anticipated that speed. During low-flow conditions, every gallon withdrawn from the river for irrigation was a gallon that never reached downstream users. Surface withdrawals didn't relieve pressure on the system, they shifted. At the same time, wetland restoration produced an unintended effect. Designed to hold water and buffer variability, many restored wetlands sat directly atop highly permeable aquifer layers. Instead of slowing water loss, they accelerated groundwater recharge. Each gallon captured was another gallon pulled underground. Dr. Amanda Winters raised concerns early. The wetlands, she warned, were acting as hydrologic sumps, funnels feeding the very aquifers draining the river. Short-term river levels near Memphis spiked after upstream releases, creating the illusion of progress. But those pulses never reached New Orleans. They vanished into the same porous sediments beneath the riverbed. By February of 2025, discharge at Tarbert Landing fell to 214,000 cubic feet per second, the lowest reading ever recorded. Quietly, the language changed. Recovery became adaptive management. Restoration became sustainable reduction scenarios. Monitoring wells in the Memphis sand aquifer showed something worse. The rate of groundwater decline was accelerating. Wells that had dropped 6 feet per year in the previous decade were now falling 14 feet per year. The system wasn't healing. It was locking itself into a new state. Engineers had a term for what they were seeing: storage deadlock. Water was present underground, but trapped in zones unreachable by wells and unavailable to ecosystems. It existed, but it couldn't be used. Then another crisis surfaced. With river flow weakened, the Mississippi could no longer push back the Gulf of Mexico. Salt water intruded upstream. In early 2025, drinking water sources in parts of coastal Louisiana showed dangerous salinity levels. As many as 80,000 people temporarily lost access to safe water. Emergency desalination units were deployed. The fix hadn't fixed the problem. It had exposed how fragile the system really was. And for the first time, a question began circulating, not in public statements, but in private meetings. Were they solving the crisis, or just... By the spring of 2025, the conversations had changed completely. No one was asking if the Mississippi River would recover anymore. They were asking how much failure could be managed without collapse. Internal reports from the Army Corps stopped using future tense language. Phrases like "will stabilize" disappeared, replaced by "may temporarily temporarily mitigate and cannot guarantee downstream consistency. Those words never reached the public, but inside the agencies, the meaning was clear. The Mississippi wasn't behaving like a river anymore. It was behaving like a leaking container. Hydrologists began comparing the Mississippi Basin to a cracked reservoir, water entering the system faster than it could be retained, disappearing through invisible pathways underground. No single intervention could seal it. Then came the satellite data. NASA's GRACE satellites, designed to measure changes in Earth's gravity caused by water movement, revealed something no surface gauge could show. The basin wasn't just losing surface flow, it was losing total water mass. Between 2022 and early 2025, the lower Mississippi Basin had lost an estimated 94 cubic kilometers of water. That wasn't seasonal variation, that was structural depletion. In simple terms, the system was shrinking. Rainfall patterns offered no relief. Storms still came, but they came differently, shorter, more intense. Instead of soaking into soil and slowly feeding the river, water raced across hardened farmland and urban surfaces, flooding briefly, then vanishing. Flash floods increased, base flow declined. The river spiked violently, then collapsed again. This pulse and drain behavior confused every existing model. Engineers couldn't plan releases because the river no longer responded predictably. Farmers couldn't plan crops because water availability shifted week to week. Barges couldn't plan routes because channels changed faster than maps could be updated. In April 2025, a closed-door workshop was held in St. Louis. Senior hydrologists from 5 federal agencies attended. No press, no minutes released. One slide from that meeting leaked weeks later. It showed 3 curves: best case, probable case, worst case. All 3 declined. The only difference was how fast. In the probable scenario, the Mississippi would stabilize at roughly 65% of its historical average flow by 2032. That level would permanently restrict shipping, eliminate millions of irrigated acres, and force population shifts in at least 4 states. In the worst-case scenario, stabilization never occurred. Instead, the river entered what scientists call irreversible channel fragmentation, sections remaining navigable, others becoming seasonally disconnected, shallow and sailing. That word, irreversible, changed everything. Once spoken, it couldn't be taken back. Public messaging still insisted on resilience. Officials talked about innovation, adaptation, long-term planning. But behind closed doors, the focus shifted to triage. Which cities could be protected? Which farms could be saved? Which ecosystems would be sacrificed? Because saving everything was no longer an option. And then one final realization settled in, the kind that doesn't make headlines but keeps people awake at night. The Mississippi River wasn't just water. It was the organizing system for food, energy, transportation, and settlement across the center of the country. If it permanently weakened, nothing else stayed where it was. And what came next wouldn't look like a disaster. It would look like slow, permanent change. Quiet at first, invisible to most, unstoppable once recognized. The question wasn't whether the river was changing, it was whether anyone was truly prepared for what replacing it would mean.